Okay, so we're going to finish up this example by writing the equation of the tangent line. Then we're going to follow this format in point slope form. So writing the equation, it's going to be y minus function evaluated at c. So again, when we plug 1 in for x, I get 0 equals the slope of the tangent line, which again we found by evaluating this limit, is 1, then x minus our c value, and our c value is 1. Alright, so when we simplify this a little bit, we get y is equal to 1x minus 1. That's the equation of our tangent line. Okay, so moving on to the second page of the notes. The slope of the tangent line to a function is very important, okay, because we are now going to kind of change the viewpoint of the slope of the tangent line, because that slope is also called the derivative of the function at that point C. Okay, so this is going to be a very important concept as you start calc in the fall. Right, derivative of the function. So when you're trying to find the derivative of a function at a particular point, right, it is related to the slope of the line tangent to the function at that point. Okay, so given y is equal to f of x and c being a number in the domain of f, the derivative of f at c is going to be written is defined as this. Okay, so there's a slight change in notation. Right? So now again, instead of using lowercase m as a slope, right, we're going to be using this notation, which means derivative. Right? The derivative of the function at c. That's what this is. It's like a little apostrophe, right? The derivative, it's not a 1. We should write that a little slightly more. Right? The derivative of the function at c can be found by taking the limit of the as x approaches c using this setup. Okay. Again, as long as the limit exists. Right? So we got to remind ourselves that just because we set up a particular limit expression doesn't necessarily mean that there's always going to be an answer. Right? Alright, so let's go ahead and apply that with this next example. Since we want to find the derivative of this function at x equals 1. Okay, so to find the derivative, make it a little bit better there, so it's a little like a little dash, right? Or explain the line as find the derivative of the function at 1. We are going to set it up as a limit as x approaches 1. We're going to set it up f of x, so that's that, so negative 4 plus 3x squared minus the function defined at c. So I'm going to plug 1 in for x, so it's 1 squared is 1 times 3 is 3, negative 4 plus 3 is negative 1. We're subtracting negative 1 all over x minus our c value. Alright, so it's going to simplify that. So minus negative 1, that's plus 1. So it's going to end up to be 3x squared minus 3. We're going to combine like terms. All over x minus 1. I can't just plug in 1 in for x. My function will be undefined, so I'm going to do a little factoring. So take out a GCF of 3 up top. So now I'm left with x squared minus 1 nothing cancels yet, so I want to go ahead and factor again. So I'm going to factor difference of perfect squares, so it's x plus 1 times x minus 1. So find the limit as x approaches 1. Cancel, or x minus 1 cancel. So I plug in 1. 1 plus 1 is 2. 2 times 3 is 6. Okay, so for this particular problem, the derivative of this function as x approaches 1 is equal to 6. Let's move on to example number 4. We want to find the derivative of this function, which is a cosine function, as x approaches 0. All right. So we want to find the derivative as x approaches 0 for this function. So that's the same as finding the limit as x approaches 0. F of x, cosine x, minus f of c, plug 0 in for x, that's just 1, all over x minus c's, x minus 0. Alright, so again, simplify this expression a little bit. So we have cosine x minus 1 over x, which again we've talked about before. Alright, again, it's one of those situations where you just got to remember, right, the limit of this particular scenario is just 0. So the derivative of the function at 0 is equal to 0. Okay, so to finish up with this last example, we have an object being dropped from rest from the top of a tall building. Right, and that free fall is described by this function, 16t squared. Right, so in the first t seconds, so find the average speed of the object during seconds 1 to 4. So to find the average speed, right, that is your difference quotient, average rate of change, which is kind of like slope. Right, so to find that average speed, we are going to take the difference of the outputs of the function at where it started and where it ended. So we're going to define it, it's going to be f of 4 minus f of 1 over 4 minus 1. Again, we are using this function, right, in accordance with our little slope formula to find the average speed of this object that is falling. So f of 4, so I'm going to plug 4 in for x. So it's going to be 16 times 4 squared, 256, and 4 in for x, you get 256, minus f of 1, plug in 1 in for x, 1 squared is 1, times 16 is 16, divided by 4 minus 1, okay, so 256 minus 16, 240, divided by 3, and then we get 80. Okay, so the average speed of the object between time 1 to 4 is 80 feet per second. Now if we want to find the instantaneous speed, specifically at time equal to 4 seconds, instantaneous speed situation is the same thing as finding the slope of the tangent line. It's the same thing. Instantaneous speed is the same thing as finding the derivative of the function at that particular t value. Okay, so average speed, we're finding it this way. Instantaneous speed at a specific time value, it's the derivative. Okay, so we want to find the derivative of the function, at 4. Alright, so that means we're setting up a limit as x approaches 4, where we have f of x minus f of 4 all over x minus 4. Alright, and we're using this setup, the derivative, limit as x approaches c of f of x minus f of c over x minus c. The limit, the derivative of the function at 4 is equal to the limit as x approaches 4 of f of x minus f of 4 for x minus 4. Alright, so f of x is 16t squared minus f of 4. We plug 4 in for t and get 256 all over x minus 4. But in this case, we're going to change it to t because we're using t. Alright, so let's go ahead and find this limit. So we could take out a 16. So it's going to be t squared minus 16. T minus 4. That's factorable, difference of perfect squares. So that's t plus 4 times t minus 4. T minus 4. T minus 4's cancel. Alright, so now we can evaluate this limit. So the limit as t approaches 4 of 16 and t plus 4 is equal to 2 plus 4 is 8. So 16 times 8, 128. So 128 is our limit, and for us, that is the derivative of this function at 4. And to answer this question, that is the instantaneous speed, right? That's how fast this object is falling exactly at 4 seconds into the free fall. 128 feet per second. Okay. Alright, so that's it for today. If you guys have any questions, please let me know. You guys have a great day.